In this video, we will discuss the concept of stress. Okay, let's take an arbitrary body, and on this body, as you see, external forces are acting. First, we try to find the internal forces in a section of this body, and for this, we make a cut. When you cut and take the free body diagram of the lower part, you see in this section we have chosen, there is a distribution of forces. You can put instead of distribution a single force and a single moment acting in the sentroid of this section, and this force and this moment can be represented also by its components. Let's take the force. So the force has two components. One is normal to the plane, the other one is in the plane, which is a normal force and a shear force. If you consider the moment vector, it can also be represented by its components. First, the torque, which is perpendicular to the plane, and by a bending moment, which is in the plane. The same is easier to see in 2D or planar cases. Here, the internal forces are shear, a normal, and a bending moment. So far, we have found the internal forces. Now we come to the concept of stress. How is stress defined? Stress is the intensity of the internal forces. And stress is defined in a plane and in a point. So let's take the same section and take this as our point. Well, we can take a small area, delta A, and the corresponding forces acting on delta A can be taken as delta F, and we now consider only now the delta F and the delta A, and with their help we try to find the stresses in this point. The first thing we do is we represent this delta F by its components. As you see, if I take the axis X, Y, and Z, you can take delta Fz, which is the normal component. Delta Fx and delta Fy are the shear components of delta F. The next we have to do is we can try to calculate the normal stress. We can take delta Fz divided by the area. That gives you the intensity of the normal force in this small area. And if you calculate the limit of this ratio for delta A approaching 0, then you find the sigma value, that is the normal stress in this point. Its direction is Z. This is how we calculate sigma Z on this small plane, and it's perpendicular to the plane. Let's take the shear forces. The shear forces divided by the area when delta A approaches 0 gives you the shear stress in this point. And as you see, shear stresses have two subscripts. The first one indicates the normal of the plane on which the force is acting. the second one gives you the direction of the shear stress. The same you can do for the next force. Let's take delta Fy divided by delta A gives you tau Zy. In this case, y is my new direction, whereas z is the same because this is the normal of the plane on which the forces are acting. As you see, in this cut, we have found three stress components, one normal and two shear stresses. Well, through the same point, P, we can make another cut, perpendicular to the previous one. In this case, my normal is in the y direction, and in the y direction, when you take the delta Fy divided by delta A, gives you sigma y, which is the normal stress, and the shear stresses are caused by the forces delta Fz and delta Fx. Well, these forces divided by the area gives you the shear components. In this case, the first subscript is the normal of this plane, which is y, and the second one is the direction of the shear stress. Well, you can make another cut. You can take this cut. This time your normal is your x direction. Delta Fx becomes your normal force, and your normal stress is calculated by delta Fx over delta A approaching 0. And in the same way, you can calculate the shear forces, shear stresses. We have taken a point, made three cuts, and on the sections we have calculated the normal and the shear stresses. The normal stresses are identified with only one subscript, and this subscript shows you the direction of the stress, whereas the shear stresses are identified by two subscripts. The first one gives you the normal of the acting plane. The second subscript gives you the direction of the shear stress. In order to be able to calculate the shear and normal stresses on a plane going through this point, well, this plane may have any angle. There are infinite number of planes going through this point. If we know these 9 components, then we can calculate the shear stresses and the normal stresses on any plane, and we can say that we know the stress state in this point. What about the unit of stress? Stress is the intensity of forces. That means force, the unit is Newton. Per area, the unit is meter square. And this unit is called Pascal. Okay, Newton per meter square is 1 Pascal, and 1 Pascal is for mechanical or civil engineers is a very, very small value. Imagine a 1 meter to 1 meter, let's say, area, and 1 Newton is acting on this. This may be used for measuring the pressure of gases or air or whatever. In mechanical and civil engineering, we need units which are like kilopascal, megapascal, and gigapascal. And that is the mostly used one in mechanical engineering. It's 10 to the 6 Newton per meter square, which corresponds to Newton per millimeter square. And it is very practical to use these units and find the stresses in megapascals. Okay. On the other hand, in the US system, we have pounds per square inch, which is called PSI, and 1000 PSI is 1 KSI. First, let's use what we have learned. We can start with the average normal stresses. Well, when you have a normal force, P, acting on an area A, well, if you take P divided by A, you find sigma, which is your normal stress. Well, to be simple, we take this distribution as uniform, and as long as the force is acting at the centroid, so this type of distribution is correct. Otherwise, if you apply the force P, for example, on this corner, well, there will be bending moments, and so the distribution will change, but we assume that it is acting in the centroid and the distribution is like that. Simple problem. Well, we have a bar, forces are acting on the bar, here 120, here 220, in the middle there are other forces. So the section is given. Question is, determine the maximum average normal stress and its location. You see, in this bar there are 3 regions. This is my first region 1. The second region is, as you see over here, that's the second region, and that's the third region. The internal forces in these regions will be different. How do I find it? I cut and take a free body diagram. Let's cut here. And this is the free body diagram. And in order to have an equilibrium, the internal force in region 1 is 120. The next cut is in the second region. In the second region, when you cut here, take the left side free body diagram, the internal force is 300 newtons. The last cut is in here in the third region. So now we take the right part, and this free body diagram gives you the internal force in the third region. And if you draw these, now we take these forces and draw a diagram of normal forces. This is region 1, region 2, and region 3. As you see, the maximum is here in region 2. It is 300. So when you have the maximum force, the question is to find the maximum average normal stress, and that is sigma max equals to F max divided by A. And if you do this calculation, you can find the value as 7.5 megapascals. Newton per millimeter square is megapascal. And we assume that the distribution is uniform. Another problem, also a very simple one. Here we have a rod. It has 3 sections and with different colors. Determine the average normal stress in different sections. So what we have to do is find the internal stresses in these 3 regions. First, we cut in yellow, and The free body diagram shows me the internal force is 400. 400 divided, now here the diameter is 80, so you calculate the stress in region yellow as 79. Region blue, you cut here, and here you have 200. How do you find this 200? This is your free body diagram. 400 in this direction, 100, 100, and 200 must be in that direction. So 200, now you have a new diameter, and this is your new stress. The pink is here. You can take the lower parts, free body diagram, internal force, new diameter, and this is the stress in the pink region. You see, region 1, 2, and 3 have different stresses. The next we're going to discuss is shear stress. We all know that shear stress acts in the surface. Take the brown shear surface A, and shear force V is acting in this surface, and the load distribution looks like this. What we do is similar. We take the shear force divided by the area and find the average shear stress. We can show different examples of shear connections. So you see here we have a bolt, and the left and the right parts are connected with the rod. And as you see, the forces acting on the bolt are shown like this, and the blue lines are the points or the surfaces where shear forces or shear stresses are acting. Well, these are my shear forces. The force acting is, if you have two forces, the force acting on each of these surfaces is F over 2, and you have the area, and so you can find the average shear stress. Well, the same. You see, there is another connection of two sheets, again a bolt, and in the plane, the force acting is V, area of the bolt, gives you the shear stress. In this example, you have a lap connection. So two sheets are maybe glued, maybe welded together. This is your shear surface, and you apply the load V, and this is a force acting on the surface. But as you see, this force and this force are not on the same direction, so there is a difference. There is a bending moment which is created, so this may cause some difficulties. So if you make a double lap shear, then the forces are balanced, and then you don't have any bending moment. Let's solve a simple problem. There is a pin connection, and as we have seen before, the blue and the brown parts are connected with a pin. The pin has a diameter of 20 millimeters, and the force F is acting is 30 kilonewton. So we can easily say that the shear forces are critical in these two, let's say, sections. So in these sections, the forces are F over 2, F over 2. What you do is take this force divided by the area, put the numbers, and you see This is 30 kilonewton divided by 2, and this is the area of the bolt, and the shear stress acting in the bolt can be found as 47.8. Another problem. There is a bar. The section is a square cross section, 20 times 20, and an axial force 100 Newton is acting in the centroid. So determine the average normal and shear stresses for sections 1,1 and 2,2. Let's forget this and take 1,1. This is very, very simple. You have the force, you have the area. What you do is take the force divided by the area and you find the normal stress. Is there any shear stress in section 1,1? No, because if you take the free body diagram, there is only a force normal to the section and my shear stress is 0. But if you take section 2 and you make the same, let's say, calculations, in order to find an equilibrium for this 100, you must have 100 here, but this 100 newtons, 1000 newtons, has now 2 components. So it can be replaced by a V component and by an N component. So that 1000 Newton is not acting normal or in the plane. It has 2 different components, so it can be calculated with the help of this angle, and we find that with this calculation that the shear force is 866 and the normal force is 500. The next step is, well, to take the normal force divided by the area. Now my area is this area. It's not this area. It has become, let's say, a little bit bigger. How do you calculate it? Here, well, the section was 20 times 20. Well, this thickness is still 20, but this becomes 20 divided by sine 30. Okay, if this is 30, so this length is 20 divided by sine 30. So what you do is you take the force 20 times this length. You take the shear force 20 times this length. Now these are your normal and shear stress values. As you see, when you have a point, let's take a point like this, depending how you cut, you can cut like this, like that, or like we did with 30 degrees. So if you tell me that you know the stress state in this point P, you must be able to calculate the stresses on any plane passing through that point. So this is how it works. So when you look at this bar and a bar with a force like this acting on the centroid, don't ever think that there will not be any shear forces. Well, there's always a combination of shear stresses passing on the planes through this point P. Okay, let's take a last problem. We have a wooden board. So this is my board, okay? And this is hung on a wall, and on the wall we have a pin. So on the board we have a hole, and we put this board and hang it on the wall and apply on this board 40 kilonewtons. So the dimensions are given, the diameter of the pin, and these width and length and everything is given. Well, the problem is to find the critical points where failure may occur. It says here, determine the stresses in the wooden board and the average shear stress in the pin. Well, in the wooden board, there may be two types of stresses. The first is, well, tensile stresses. You apply here 40, and so you see this section is the smallest section. You take this force and calculate this section, divide it and find the normal force. Well, the next possibility is when you apply that 40, the next possibility is that the wooden board is cut like this. So if this length is too small, so there may be a cut due to shear forces in these yellow sections. And what about the pin? The pin is easy, you know. The pin will be cut like this, and we have to calculate these three stresses. Let's do it. Let's start with the shear stress. Shear stresses act on these two sections. So the force acting is 40,000. So the area can be calculated. Well, the thickness is 10 millimeter, and this length is 20 millimeters, and we have two sections. 2 times 20 times 10 millimeters square is the total area. Well, the calculations gives us 100 megapascals. 100 megapascal is the shear stress acting on these sections. If the wooden material has a strength which can withstand this stress value, there will be no failure. The next is, as we have discussed, the normal stresses in these sections. So here we have altogether 40, and this diameter is 15. The remaining area is 40 minus 15. This is the thickness, this is the force acting, and the normal force on these surfaces or sections are 160 megapascals. Okay, that's also fine. Well, the last one is the shear stress in the pin. Force is the same. The diameter is 15, that's the area, and that's the stress in the pin. It's higher than those stresses, but don't forget that this is steel, a much stronger material. Well, that's the end of this video. In this video, we learned what stress is, made a definition, and showed the two types, the normal and the shear stresses, how they are calculated, and solved a couple problems. So, thanks for listening, and in our next video, we will make simple mechanical design by using this knowledge about stress.